Okay, anybody else have any questions or comments regarding the exam or anything else? We're not going to be able to go over the exam the way we did for exam 1 because I don't have a way to hand it back to you. So I haven't figured out how I'm going to deal with that yet. I'll see what some common errors were and maybe discuss those. RP, go ahead.
Were the fill-in, like the, what is it, the short, not the essay questions, the ones where it were 2 points, were those automatically graded, or are you gonna have to look at those?
Those were automatically graded. The fill-in questions were automatically graded. That's why I said for the spelling, if you spell it wrong, it's gonna mark you off wrong.
Okay, so like we wouldn't be able to get like any partial credit or anything on
I
them?
actually, as I'm grading it, I can see what the computer marked you off for. So I am going back and adding some partial credit for it. If it's a misspelling, if it's like obviously just a mistype, a typo type of error, I'm giving full credit for that. But if it's an obvious misspelling, like you didn't know how to spell it, I'm giving partial credit. Whereas the computer was taking everything off. So yes, I am going in and giving partial credit for those.
Okay, thank you.
So the points that were graded by the computer was out of 60. So you have an idea of how you did on that part, and then I need to go through and grade the rest. Any other questions? Okay, so now as we finished the second midterm and we get into the last few weeks of the class, the last few chapters, this is when it starts to get a little more interesting and a little more applied. This is where we start pulling everything together. So did you guys, you got my email about printing out the table, right? You guys all have the table with you. So this table is going to be with us for the next 2 chapters. So we're on chapter 8 now and then chapter 10. So we're going to be talking about responses to exercise and adaptations to training. So taking everything we've learned so far about the muscles and the metabolic systems and the heart and all that terminology, we're now going to apply it and actually talk about how the body responds to exercise and how the body responds to training, which is exercise physiology. Okay, so we have to talk about how I'm using the terms exercise and training differently. So normally the way people think about the differences between the terms exercise and training would be to say that exercise is more recreational and training is more towards a purpose or a goal like an athlete would do. And it is possible, and we do use the terms that way, but in this class, we're going to be using the terms in a slightly different way. So let me explain to you how I'm going to be using the terms exercise and training. Okay, when I use the term exercise, I'm referring to an acute bout of exercise. Like if you start running right now, how is your body going to respond? How is your heart rate going to respond? Your stroke volume, your cardiac output, your AVO2 difference, your VO2 max, your lactate threshold. How are all of those things going to respond if you start running right now? Okay, that's what this chapter 8 is about. Chapter 10 is about how your body adapts to training, to endurance training. So meaning if you were to run 5 days a week for a year, how has your body changed from that training? How did your heart change? How did your blood change? How did your lactate threshold change? And how is that going to affect how those things respond to exercise? So I'll explain that more when we get to that chapter. But so exercise is referring to a single bout of exercise, how your body responds to you starting to exercise in the moment right now, acute. Training is how your body adapts over time to a repeated chronic training stimulus. And chapter 10 will talk about adaptations to endurance training. When we get to chapter 11, which will be our final chapter, that's adaptations to anaerobic training, which will include high intensity interval training and resistance training. Okay, and those are the only chapters left that we're doing. Okay, so it's going to be a lot more applied. Okay, so starting with your table, let me show you how this table is working. So down the left side of your table, you have all the different variables we've been talking about. Heart rate, stroke volume, cardiac output, lactate threshold, AVH difference, and it goes all the way onto the back. So we've learned all of that terminology. Okay, so those are the different variables we're going to be discussing. Then the first column says what happens to these variables as you increase your exercise intensity. And you're going to have arrows there. It's either going to be increase, decrease, or stay the same. And then you have a box to explain why. So what's happening to your heart rate as you exercise, as you increase your exercise intensity? Is it increasing, decreasing, or staying the same? And then we're going to explain why. And we're going to go through and we're going to fill in both of those columns on both sides of the table, and that's going to be chapter 8. Okay, then we're going to go to chapter 11, which is adaptations to aerobic training. And we'll go to the next column with what happens to these variables with training: increase, decrease, or stay the same, and why. So we're going to spend the next 2 chapters filling out this table in its entirety. Okay, and this is going to be full of information that you're going to want to keep for 446. Okay, so any questions about any of that and how that's going to work in the direction we're going? Okay, you're going to want separate paper to take notes on in addition to this table, because I'm going to be giving you more information than you'll be able to fit into the table. Okay, so take notes on the table, but also have separate paper you can take notes on, and you're going to be printing out a bunch of these tables and filling them out over and over again. So we'll get to that later too. Okay, so no questions? We're good? Okay, so I'm going to go on the table and start with resting heart rate. Okay, AJ, what's a normal resting heart rate?
60.
What's the normal resting heart rate range?
60 to 100.
60 to 100, right. So, and we talked about a trained person will tend to be on the lower end of that range, 60 to 80. An untrained person will tend to be on the higher end of that range, 80 to 100. We'll talk about why that is when we get to the training chapter, because training is going to affect your resting heart rate. Right now, we're talking about exercise affecting your resting heart rate. Okay, so as you increase exercise intensity, so let's say you're on the treadmill going from 4 miles per hour to 5 miles per hour, 6 miles per hour, 7 miles per hour, you're increasing your exercise intensity. What's happening to your resting heart rate? Is it increasing, decreasing, or staying the same?
Increasing.
Increasing. Okay. Does everybody agree that it's increasing?
It's to stay.
So why does it stay the same? That was Sung, that was you that said it stays the same, right?
Oh yeah. Because isn't resting heart rate just like how to explain it? Like it's just gonna be between like the 60 to 100 beats per minute. So for what you said earlier, a trained athlete, it'll just stay either at 60 to 80, and then for untrained, it's gonna be in between 80 to 100. Like it doesn't, like exercise won't affect the heart rate. I don't know how to explain. That's all I have.
Okay. So I had about 12 people that I could see nodding their head and agreeing that resting heart rate would increase with exercise intensity. And I have Sung saying that it would stay the same. Can someone else chime in with what you think? Increase, decrease, or stay the same?
I think it would increase because you're increasing intensity. So that would, in order to meet that work put, you have to increase your output.
Okay, I see a lot of people nodding in agreement with that. So are we in agreement that resting heart rate increases as exercise intensity increases?
Of course.
I think it stays the same because resting heart rate is like for a person, if their resting heart rate is like 54 beats per minute and then they exercise and then they rest, their resting heart rate's still going to be 54. Opposed to someone who trains, if they have like 54 and then they train constantly, then their resting heart rate could go down to like 50.
Oh wait,
Go ahead.
I think it's actually the opposite, because if you're more trained, then it would be lower. But this is like at rest, you're saying, right?
No. Okay, separate the trained from untrained. Trained from untrained right now does not matter. You're exercising, you're increasing your exercise intensity. What is happening to your resting heart rate? Is it increasing, decreasing, or staying the same as you speed up on the treadmill?
It's going to increase. It increases.
Justin, go ahead.
Wouldn't it stay the same? Because like that would be your base value when you exercise. That would be your base value as you go into your submax heart rate as exercise intensity increases.
Armand, what do you think?
I think it'll increase because then if you're going very fast and it's intense, then you're probably using the bicarbonate buffer and you have to get the carbon dioxide out. And for that, breathing rate increases and your heart rate increases with that, right?
Okay, Ariel, what do you think?
When we exercise, we have epinephrine, and that is going to cause vasoconstriction, and that's going to cause our heart rate to go up. We also have an increase in sympathetic system. So we have the cardiac nerve, the sympathetic cardiac nerve, that's going to help increase our heart rate.
Vanessa Palafox, you have your hand up.
I agree with Ariel. Exercise will decrease PNS activity, which will basically cause the vagal tone to decrease and will cause our heart rate to increase. And I'm connecting this to blood pressure as well, like the chart that we learned in, I believe, chapter 6, where if we exercise, blood pressure increases, and we know that heart rate is connected to blood pressure. So that's how I'm connecting it.
Okay. Emily, what do you think?
I think that heart rate's going to have to increase if your intensity is increasing because you have muscles and they're in demand of oxygen and they need carbon dioxide removed. So in order for that to happen, you have to increase your, like, how much blood is flowing through the body, which is, cardiac output and all of that. So I agree that it has to increase. It wouldn't, if you were like increasing your intensity, I guess like the resting would mean that it's confused. There's like overlap, but if you're increasing intensity, your heart rate has to increase.
Okay. This is very interesting because I'm obviously staying on this because there's something wrong here. And I'm getting basically the same answer from everyone, but I keep going on it because I'm waiting for you guys to figure something out. And so these next few weeks is going to be a lot of critical thinking. Okay, we've already learned the concepts and the processes and the terminology, and now we need to apply it. And applying it takes some critical thinking, which is what I'm trying to get you to do at the moment. Gwen, go ahead, please.
I think it'll stay the same because it's resting heart rate. So it has to do with when you're at rest. And when you exercise, that's no longer your resting heart rate, that's your submax heart rate. So your resting heart rate is unaffected by exercise. And it's affected by training, but not by acute exercise.
Exactly. So think about it this way. Let's say your resting heart rate is 70 beats per minute. Okay, we understand that's your lowest heart rate when you're relaxed and resting. If you get on the treadmill and start jogging, 4 miles per hour, 5 miles per hour, 6 miles per hour, 7 miles per hour, yes, your heart rate is going to increase because of all those things you said. A decrease in parasympathetic system, increase in sympathetic nervous system activity, cardiac nerve, epinephrine. And your heart rate is 140 while you're jogging. Is that your resting heart rate? What heart rate is that?
Submax.
Submax. We have a resting heart rate, which is our lowest when we're resting. We have a max heart rate, which is the highest our heart rate can go at our highest intensity. Everything in between is submax. So when you're running and your heart rate is increasing, that's not your resting heart rate that's increasing. That's your submax heart rate that's increasing. Okay, so you have to think about the terminology that you're using. If your resting heart rate is 70 beats per minute and you start increasing your exercise intensity, your submax heart rate is going up. Your resting heart rate is not affected. Your resting heart rate is still 70. You're just not at it anymore. Does that make sense? Okay. So what happens to resting heart rate as exercise intensity increases? Increase, decrease, or stay the same?
Stay the same.
Is the
It
same.
stays the same. It's not affected by exercise intensity. It will be affected by training because we said trained people will have a lower resting heart rate. It's not what we're talking about right now. What we're talking about right now is how does it respond to increasing exercise intensity? Resting heart rate is not affected by your exercise intensity.
So is the question, it's kind of like what happens to your resting heart rate if you just increase your exercise intensity one time?
Yeah.
Okay.
When we're talking about exercise, we're talking about one bout of acute exercise with increasing intensity. So not even steady state, like staying at 6 miles per hour.
Mhm.
So it should say on your table with increased exercise intensity, right? With increased exercise intensity. So that's how we're answering all of these. What happens to your resting heart rate as you increase your exercise intensity? Resting heart rate not affected. Everybody okay with that? Okay. Next one is max heart rate. How do we estimate max heart rate?
220 minus your age.
220 minus your age, okay? So the question is, what happens to max heart rate as exercise intensity increases? Does it increase, decrease, or stay the same?
Stays the
Stay
same.
the same.
Stay the same. Why?
Stays the same.
Because it's 220 minus your age.
It depends on age. It does not depend on exercise intensity, and it doesn't even depend on fitness, right? So that one's not even going to be affected by training because it's 220 minus your age. Your training status is not even in there anywhere.
So in a sense, you would say it's like an independent variable?
No, independent variable has to do with research. It just means it's
Okay.
not affected by exercise intensity.
Gotcha.
An independent variable in research is something that you're manipulating. That's not the right term here. Okay, so I don't know if you can see on my table, I have resting heart rate, stays the same, not affected by exercise. Max heart rate, stays the same, not affected by exercise. Okay, so now we're at submax heart rate. What happens to submax heart rate as exercise intensity increases? Does it increase, decrease, or stay the same?
Increase.
Increase.
Increase, why?
Either withdrawal of the parasympathetic nervous system, so decreasing vagal tone, or increased activity in the sympathetic nervous system, meaning epinephrine is acting on the SA node, or increased activity of the sympathetic cardiac nerve.
Exactly. So we have those three things that act on the heart rate that allow it to increase as intensity increases, and we have a graph for that, right?
Yeah.
Okay. So that Y explanation goes in that Y box. Why submax heart rate is increasing as intensity increases. Withdrawal of the parasympathetic system, increase in activity of the sympathetic nervous system, and the details that go along with that. Okay, that's not new information. We're just applying it here. Okay. Next one is AVO2 difference max. So we have on the table AVO2 difference max and AVO2 difference submax. There's also, so just like with heart rate and VO2, there's a resting, there's a max, and there's a submax. Okay, I don't have resting on here. We're not going to talk about resting. We're just going to talk about max and submax. So AVO2 difference max is your muscles. Well, let me get a definition first. Alexis, what is the definition of AVO2 difference?
AVO2 difference. Oh yeah, AVO2 difference is the difference of oxygen content between arterial blood and venous blood.
Perfect. And what does it reflect?
It reflects the intensity that one is working at.
Okay.
Because
it reflects oxygen consumption of the muscle, right?
Okay.
The more oxygen the muscle consumes, the bigger the difference there will be in the oxygen content, but that also reflects intensity. Okay, so AVO2 difference max then is your muscle's maximum capacity to consume oxygen, right? So what happens to AVO2 difference max as your exercise intensity increases? Does it increase, decrease, or stay the same?
Stay the same.
Stay the same, why?
Because that's your max, so it doesn't change.
Right, so anything where we have a resting level and a max level, and anything in between is submax. The submax is what's changing as you change your exercise intensity, not the resting and the max. If anything, those are affected by training, not by exercise intensity. It's the submax that's affected by exercise intensity. Okay, a max is a max. Tatiana, go ahead.
What was the definition of the AVO2 difference max again?
Well,
oh, how'd you say? You said something. It was like
well,
the
we
max.
said AVO2 difference, the difference in the oxygen content of the two areas reflects oxygen consumption at the muscle.
Okay.
So AVO2 difference max would reflect the maximum capacity of the muscle to consume oxygen.
Okay.
Okay, so AVO2 difference max, not affected by exercise intensity. AVO2 difference submax, increase, decrease, or stay the same?
That would increase.
Okay, why?
Because as intensity increases, you're consuming more oxygen.
Right. As exercise intensity increases, the muscle consumes more oxygen, which is going to give you a bigger difference in oxygen content between the artery and the vein. Everybody good with that? Okay. Next, we go into stroke volume. We have max stroke volume on here and submax stroke volume. Okay, so well, let's do a definition first. Evelyn, what's the definition of stroke volume?
Stroke volume is end diastolic volume minus the end systolic volume.
Okay, what is it in words?
I'm sorry, I got like a message from the school.
Okay.
An
amount of blood.
An amount of blood clumped by the left ventricle per beat.
Per beat, good. Okay, so stroke volume max then would be the maximum amount of blood the ventricle could pump in one contraction. How is max stroke volume affected by increasing exercise intensity? Does it increase, decrease, or stay the same?
The max would stay the same because it's the max.
Right, maxes, I don't think there's any max that's going to be affected by exercise intensity. Exercise intensity is going to affect submax. Okay, it's just not affected. Submax stroke volume. How is submax stroke volume affected by increasing exercise intensity? Increase, decrease, or stay the same? Gwen says increase, Rachel says increase, Emily says increase, Roxanne says increase. That's true. Stroke volume submax is going to increase as exercise intensity increases. So now we need to talk about why, okay? And that's where it's going to get a little more complex. I'm going to put the whiteboard up. So the question we're asking is, what's causing the increases in submax stroke volume during exercise? So first thing we need to do is write the formula, because if we want to talk about what's affecting stroke volume, we have to talk about the things that affect stroke volume. Stroke volume equals, I'm going to spread this out, end diastolic volume minus end systolic volume. Okay, Nina, what's the definition of end diastolic volume?
I don't remember.
Okay, these were on your test. These are important, very, very important terms. Jason, what's the definition of end diastolic volume?
The amount of blood in the left ventricle after diastole.
After diastole, and what is the ventricle doing during diastole?
Relaxing.
Relaxing and filling, so that's when it's full. Okay, Andrew, what is the definition of end systolic volume?
It's the amount of blood left in the left ventricle at the end of systole.
At the end of systole, and what is the ventricle doing during systole?
It's contracting and emptying.
Contracting and emptying, so that's when it's empty. Okay, so we already know that stroke volume is going to be increasing. We're talking about submax stroke volume. It's going to be increasing as intensity increases. In order to do that, we need to get more blood into the ventricle when it's filling, and we need to have less blood left in the ventricle after we contract it. Okay, so we want end diastolic volume to be high, and we want end systolic volume to be low. Okay, end diastolic volume depends on two things, and end systolic volume depends on two things. End diastolic volume is, remember, how much blood we can get into the ventricle when we're filling it up. Okay, that's going to depend on venous return. What are some things that will, so we need venous return to increase so we can get more blood into the heart. What are some things that will increase venous return?
Vasoconstriction.
Vasoconstriction.
Skeletal muscle pump.
Skeletal muscle pump and
Respiratory pump.
respiratory pump. MM stands for muscle. So that's not new information. We already learned that, right? Skeletal muscle pump is activated by muscle contraction, right? Which is happening because we're exercising. So we start exercising, we're contracting our muscles, that activates the skeletal muscle pump, which increases venous return. That increases end diastolic volume, which will increase stroke volume. Everybody follow that? Questions? Respiratory pump is increasing or is activated because we've increased our ventilation rate. What caused us to increase our ventilation rate?
Too much CO2 in the lungs.
Could be carbon dioxide from the bicarbonate buffer. Could also be epinephrine, right? Those are two things that cause increases in ventilation rate, carbon dioxide and epinephrine. I'm gonna put epinephrine here. You could also put carbon dioxide and it would work. Okay, it would just make this map more complicated. Okay, that's happening. Why is the epinephrine release happening?
Increased exercise intensity.
Increased sympathetic nervous system activity due to exercise. Okay, so you start exercising, sympathetic nervous system becomes more active, releases epinephrine, causes an increase in ventilation rate, which activates the respiratory pump. This increases venous return, which increases end diastolic volume, which increases stroke volume. Do you follow that? Stop me if you're confused. What's causing vasoconstriction?
Epinephrine.
Acting on
The arterials.
epinephrine is because of, I'm just going to do this. Increased sympathetic nervous system activity due to exercise. Okay, none of that is new information. We're just connecting it to stroke volume. Do you have any questions on that so far? Okay. Okay. I'm going to have another branch here for end diastolic volume, but I'm going to skip it for now and I'm going to come back to it later. I'm going to go over to end diastolic volume, end systolic volume now. So, what did we say is the effector for stroke volume?
Left
ventricular
Left ventricular myocardium. The more forcefully we can get that muscle to contract, the more blood we can get out, which is an increase in stroke volume, which means there's less blood left in, right? The more forcefully we can contract that muscle, the less blood we're going to leave inside it. Make sense? So that's where the left ventricular myocardium is going to come in. Okay, so we're going to use the term increased left ventricular contractility, which basically just means contraction strength. Coming from the left ventricular myocardium. What's causing the left ventricular myocardium to increase its contraction strength?
Increase in SNS activity.
Causing the release of epinephrine. So I'm just going to connect this here. Is everybody okay with that? Save me some time and energy. You start exercising, sympathetic nervous system becomes more active, releases epinephrine. That acts on the left ventricular myocardium to increase its contraction strength, which is going to cause an increase in stroke volume, more blood out, meaning less blood is left in. So you have a decrease in end systolic volume. Everybody okay with that? Okay. The other thing that's going to affect end systolic volume, the amount of blood that's left in the ventricle after you contract it, is how much resistance the heart is working against. Okay? The heart, the ventricle is trying to move blood out. If it's working against a lot of resistance, it's going to be hard to get the blood out, which means more blood is going to be left in. If we can decrease the resistance we're working against, we can get more blood out, which means less blood will be left in. Okay, and that's what's happening during exercise. Okay, we need a decrease in resistance so we can increase our stroke volume, which is going to mean a decrease in end systolic volume. Okay, so we need here decreased resistance. Okay, I'm saying resistance here instead of peripheral resistance because this is specifically resistance against the left ventricular contraction, whereas peripheral resistance is more towards the exercising muscle. It's peripheral, it's distal. This is more proximal to the heart, but I'll kind of use the terms interchangeably. If you were to say peripheral resistance here, I wouldn't mark it wrong, but it's really just resistance. Okay, but it's the same idea. So what would be causing a decrease in resistance?
Increased radius.
Yes, what's the term for that?
Vasodilation.
Increased vessel radius. Vasodilation. What's causing vasodilation?
The 6 local conditions of the exercising muscle.
Yeah.
And you should be able to list those. I'm not going to take the time for that right now. You should know those. So those local conditions of the exercising muscle are being caused by exercise. Right? You start exercising. I'm going to add in here muscle contraction. So you start exercising, you're contracting your muscles. That causes those local conditions that we can list. which triggers vasodilation. Actually, sorry, I'm going to add in here arterial increased it's going to trigger arterial autoregulation, which is going to cause vasodilation. That's going to increase vessel radius, which is going to decrease resistance. That means it's going to be easier for the heart to get blood out, which means less blood will be left in, which is an increase in stroke volume. Okay, so all of this is explaining how an increase in exercise intensity is causing an increase in stroke volume, step by step. Questions so far? Okay, I have one more branch here to add under end diastolic volume, and that is increased left ventricular distensibility. So we have venous return, we have left ventricular distensibility, left ventricular contractility, and decreased resistance. Okay, so the increased left ventricular distensibility. Distensibility refers to the ability to stretch. Okay, so if you think about, we'll go back to our water balloon example. Water balloons, when they're empty, are small. When we fill them with water, they stretch to accommodate the water, right? So the ability of the balloon to stretch affects the amount of water we can get into the balloon. Okay, so think about that as the ventricle. The ability of the ventricle, the walls of the ventricle to stretch will affect how much blood we can get in there, which is the end diastolic volume. Okay, so when we're filling the water balloon, if we take that empty water balloon and we put it over the water faucet and turn the water on, is the ventricle, is the balloon stretching first and then the water's coming in? Or does the water coming in cause the ventricle to stretch? Cause the balloon to stretch?
The water, it causes the stretch.
The water coming into the balloon causes the balloon to stretch. So same thing with that left ventricle. It's not going to stretch in anticipation of the blood coming in. The increased venous return, the blood coming into the heart, is going to cause the ventricle to stretch. Okay, so that means this increase in venous return, which is causing an increase in end diastolic volume, is going to then cause the ventricle to stretch. Okay. The increase in end diastolic volume due to the increased venous return by itself is going to cause an increase in stroke volume, independently of anything else. You bring more blood into the heart, you get more blood out of the heart. But in addition to that, that increased blood coming into the heart is going to stretch the ventricle, distensibility. The thing about that is, think about our skeletal muscle. If we stretch our skeletal muscle, how does it respond? What's its immediate response?
It contracts.
It contracts. What's that called?
The stretch reflex.
Stretch reflex. When you stretch a skeletal muscle, it responds immediately with a contraction. The cardiac muscle does the same thing. When you stretch it, it responds immediately with a more forceful contraction. But in the cardiac muscle, we don't refer to it as the stretch reflex. We refer to it as the Frank-Starling mechanism. So the Frank-Starling mechanism is the cardiac muscle. When it's stretched, it responds with a more forceful contraction. It's basically the stretch reflex, but in the cardiac muscle. So the Frank-Starling mechanism is when you stretch the cardiac muscle, it responds with a more forceful contraction. So that means we have an increased venous return filling the ventricle, which is going to stretch the ventricle, which is going to trigger the Frank-Starling mechanism, which I have to abbreviate here because I don't have space, but I told you what it stands for over here. Okay, that Frank-Starling mechanism is going to increase contraction strength, which is going to be an increase in stroke volume and a decrease in end systolic volume. Questions about that pathway?
Yeah, it might be a silly question, but this is all in regards to the left ventricle, right? So
Yeah.
is there also stretching occurring in the right ventricle because that's receiving just as much blood?
Possibly, but we're not concerned with what's happening in the right ventricle. Stroke volume is the amount of blood coming out of the left ventricle. So this entire thing answers what's causing the increases in stroke volume during exercise. Okay, so like we did with blood pressure, we built it this way, we can simplify this, right? They all start with exercise and end with stroke volume. There's some overlap here. How many unique pathways are there from exercise?
2.
2, what are they?
Increase sympathetic nervous system activity and muscle contraction.
Okay, so the increased sympathetic nervous system activity is going to cause a release of epinephrine, which is going to cause 1, 2, 3 different things. The muscle contraction is going to do 2 different things. It's going to activate the skeletal muscle pump, and it's going to activate arterial autoregulation. Okay, so we're going to flip this over and simplify it into a concept map. Okay, so keep this off to the side and help me build the map. It's going to start with exercise at the top and end with increased stroke volume at the bottom. It's going to either go through an increase in end diastolic volume or a decrease in end systolic volume. But keep in mind that the decrease in end systolic volume comes after the increase in stroke volume. We don't know how much blood is going to be left in the ventricle until after we empty it. Okay, so that one's going to, so the end systolic volume is actually not going to end up on the map, but that'll make more sense when we draw it. Okay, so keep this. You should have it written on paper, put it off to the side. If you need to screenshot it real quick, do that. So I'm going to erase it and we're going to flip it over. Okay. Starting with exercise at the top. How many different pathways are we going to have?
2.
What are they?
Increase sympathetic nervous system activity and muscle contraction.
Okay, let's do the muscle contraction pathway first. How many different things, how many different pathways do we have coming off of here?
2.
What are they?
Six local conditions.
And
The
skeletal muscle pump.
Skeletal muscle pump. Okay, so when we're building this, remember we have to keep in mind where the overlaps are going to be so that we don't cross lines. So I know that my skeletal muscle pump is going to lead to venous return, which is also going to be connecting to the sympathetic side. So I need to put my muscle pump in the middle so that I can connect it to the other side without crossing over. Okay, so I'm going to put the skeleton, I'm going to do this branch first. Okay, what does that cause?
It's going to cause an increase in venous return.
which causes
Increase in end diastolic volume.
which causes
Increase in left ventricular distensibility.
Okay, yes, but first let's just do increase in stroke volume. Because remember that the increase in end diastolic volume independently will cause an increase in stroke volume, regardless of anything else. You get more blood into the heart, you're gonna get more blood out of the heart. Okay, but in addition to that, it's also triggering another pathway, which is increased left ventricular distensibility. Actually, I should do that on the other side. Sorry. Let me move that. I always put it on this side, and I always regret it. Let's try it on this side, because it's going to connect. Increased left ventricular distensibility will cause what?
The Frank-Starling mechanism. Is there a reason why you blocked the increased stroke volume?
Just because that's where all the pathways are going to end.
Okay.
Triggers Frank-Starling mechanism, which causes
Increased left ventricular contractility.
which will cause an increase in stroke volume. Okay, I'm not putting a decrease in end systolic volume here, because remember that the decrease in end systolic volume is the amount of blood in the ventricle after we empty it. So the increase in stroke volume is going to come before the decrease in end systolic volume. So if it goes anywhere, it would go after this, and we don't care what happens after that. So I'm not going to put it on here. If logically you're thinking about it in terms of the formula that we wrote out, if you put a decrease in end systolic volume here, I will not mark that wrong, because I understand the logic of what you're following. It doesn't belong there, but I won't mark it wrong. Okay, questions on this so far? Okay, let's go back to the other branch of muscle contraction. What else is muscle contraction causing besides the skeletal muscle pump?
6 local conditions.
Local conditions at the exercising muscle, and I will assume you can list those. What does that cause?
Increased arterial autoregulation.
Which causes
vasodilation.
Which causes
an increased vessel radius.
Which causes
decreased resistance.
You could put peripheral resistance there. I won't mark it wrong. Okay, but I'm going to use just resistance. So you're contracting your muscles. You create these local conditions which triggers arterial autoregulation. You could put the details of the chemoreceptors in here too if you want. Arterial autoregulation causes vasodilation, which is an increase in vessel radius, which decreases resistance, which causes an increase in stroke volume and decreases in systolic volume. Questions on this side of the map? Okay, for increased SNS activity, how many branches do we have?
1.
What is it?
Epinephrine.
How many branches do we have from that?
3.
What are they?
Epinephrine's going to cause an increased ventilation rate. It's going to cause the arterioles to vasoconstrict. And there's a third one.
The left ventricular.
Myocardium. Yeah.
Okay, so does it matter which one I put where?
Yeah, because they can't cross over on the map.
So what needs to be on the inside?
The left ventricular myocardium. Because of the increased left ventricular contractility, which is caused by the Frank-Starling mechanism.
No, it's caused by epinephrine in this case. But what is going to connect to the middle branch here? What is going to, don't we have things that are going to connect to venous return?
Would it be the left ventricular myocardium?
Would be the arterioles.
The left ventricular myocardium is the only one of these 3 branches that's not going to connect to venous return. What are our other venous return mechanisms besides the skeletal muscle pump?
Increased ventilation rate and arterioles.
The ventilation rate causing the respiratory pump and the arterioles vasoconstricting. Those 2 are going to connect to venous return, so those 2 have to be on the inside. The left ventricular myocardium is not going to connect here, so that one needs to go on the outside. Okay, so let's put increased ventilation rate here. Which is going to cause, it's going to trigger what?
The respiratory pump.
Which is going to cause what?
Increase in venous return.
Okay, so I'm just going to connect it there. What's the other branch that goes here for epinephrine?
Arterioles.
Arterioles. And how do the arterioles respond to epinephrine?
Vasoconstriction.
Which is going to cause what?
An increase in venous return.
I'm going to connect it there. Okay, and what's the third branch over here for epinephrine?
Left ventricular myocardium.
And how does that respond to the epinephrine?
Increase in contractility.
Increasing in contraction strength, which I can connect here. Okay, so that increase in contractility is being caused by 2 separate things. The Frank-Starling mechanism is contributing to contraction strength, and the epinephrine is contributing to contraction strength. Those are 2 separate pathways. Okay, so this concept map is your answer in the Y box on your table. Why? What is causing the increases in submax stroke volume during exercise? Okay, obviously you can't fit this entire table, this entire concept map into that box on the table. So make a note there that this table goes there, and in a minute I'll give you a shortened version to put in there. But while we have this map up, I want to point something out to you. Do you have any questions before I point something out to you?
How did you define distensibility again?
The ability of the ventricle to stretch, the ventricular wall to stretch.
Thank you.
Distensibility is stretchability, basically. Okay, so what I want you to notice is that over here we have vasodilation, and over here we have vasoconstriction. How is it possible that both of those are occurring during exercise?
Sympatholysis.
Sympatholysis.
Well, sympatholysis dictates that we have vasodilation instead of vasoconstriction.
There's
So how is it
vasodilation.
possible that we have both?
Vasodilation is at the exercising muscle and at the skin, and vasoconstriction is everywhere else.
Everywhere else. Okay, so we have vasodilation and vasoconstriction both going on at the same time in different areas of the body. They are both contributing to increases in stroke volume in different ways. Okay, the vasodilation at the exercising muscle is contributing to increases in stroke volume by decreasing resistance. Vasoconstriction is contributing to increases in stroke volume by increasing venous return. This sounds like it would be a really good exam question. How is it possible that vasodilation and vasoconstriction are both occurring during exercise, and how are they both contributing to stroke volume? Or do they contribute to stroke volume? Or which one is occurring during exercise, and how is it affecting stroke volume? You need to know that they're both happening and they're both affecting stroke volume. Okay, so again, I'm not going to grade you on drawing this map, but being able to draw this map is going to help you answer questions about it. Questions on this map? Okay, so this would be a long form version, which if we were in class, I would probably test you on drawing. Let me give you a shorter answer. I'm going to erase this, so take a screenshot if you haven't yet. You good? Okay, I can't go back to my old page, so I'm just going to clear this. Short version of why is stroke volume increasing during exercise. Would include this. What are the 4 things that go here? Increased. What does end diastolic volume depend on?
Venous return.
Okay, what goes in the next one?
Increase left ventricular distance.
Okay, and what does end systolic volume depend on?
Increased left ventricular contractility and decreased resistance.
Okay, so the short version of what's causing the increases in stroke volume during exercise is an increase in end diastolic volume due to increased venous return and increased distensibility, and a decrease in end systolic volume due to an increase in left ventricular contractility and a decrease in resistance. Okay, that's the short form answer that you can fit in your Y box on the table. But understand that there's a lot of detail that goes into this that you should know. Make sense?
Which box are we putting this into? The max?
On your table, yeah, we're talking about submax stroke volume.
Okay.
Increases with exercise, and this is the short explanation of why. And then you also have a much longer, more detailed explanation of why. Questions? Okay, I'm going to continue on with the next couple. Max cardiac output. Christian, what is the definition of cardiac output?
That's how many beats per minute, right?
Beats per minute, it would be heart rate.
Oh, bad. It's escaping me right now.
Okay, Pam, what is the definition of cardiac output?
It's amount of blood in the left ventricular. No, it's amount of blood per minute. It's Q equals HR times stroke volume.
Okay, so cardiac output is the amount of blood pumped by the left ventricle per minute. It depends on heart rate times stroke volume, okay? I cannot express enough how important this terminology is. You will not understand anything in this chapter or the next chapter if you don't understand this terminology. Okay, so please, 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 if you don't know the terminology, work on it, work on it, work on it, or none of this is gonna make any sense to you. You're gonna be memorizing random words that mean nothing, which is, you're missing the entire point of this class. I could just give you this table filled out and you could memorize it. Okay, save me a lot of time and effort. It's not what I wanna do. I want you guys to understand what's happening in your body during exercise. You need to be able to use these terms in order to do that. Okay, so please, those are terms you should have known for the midterm. If you haven't learned them yet, you've got to put in the time to learn them so that we can use them effectively. Okay, so cardiac output is the amount of blood pumped by the left ventricle per minute. So we're going to talk about max cardiac output, and I don't have it on your table, but underneath max cardiac output, you should add another box for submax cardiac output. Okay, so max cardiac output will be the maximum amount of blood that the left ventricle can pump in 1 minute. What do you think happens to max cardiac output as your exercise intensity increases? Does it increase, decrease, or stay the same?
Stay the same.
Stay the same. Why?
Because it's your max.
It's a max. Maxes are not affected by exercise intensity. It will be affected by training, but it's not going to be affected by increasing your speed on the treadmill from 5 miles per hour to 6 miles per hour. It's not going to affect your maximum capacity to pump blood. Okay, it's going to affect your submax. Okay, so max cardiac output, not affected. Submax cardiac output, what happens?
It increases.
It increases. Why?
Because either your heart rate can go up and or also your stroke volume can also go up.
Exactly. If you want to talk about what's happening to cardiac output, you have to talk about what's happening to stroke volume and what's happening to heart rate. But let me go back and add detail here. I can't change the size of this, but talking about cardiac output submax equals heart rate submax times stroke volume submax. If we're talking about, oh, actually, I'll go back and do that in a second. Let's go back and do this. Cardiac output max then would equal heart rate max times stroke volume max. Okay, what happens to heart rate max as your intensity increases?
Stays the same.
Stays the same. What happens to stroke volume max as intensity increases?
Stays the same.
Stays the same. Therefore, cardiac output max stays the same because heart rate max and stroke volume max stay the same, not affected. If we look at submax, what's happening to heart rate submax as intensity increases?
It increases.
It increases. Lizette, why?
Is it because everything else is increasing too?
Arpi, why?
Can you repeat the question, please?
Why is heart rate submax increasing with exercise intensity?
Because it's not your max, you're trying to reach it, like it's on the incline.
Tatiana, why is heart rate increasing? Shannon, why is heart rate increasing? Armand, why is heart rate increasing?
Because epinephrine is released.
And?
The increased sympathetic nervous system activity.
And?
The specifics of epinephrine and what it does.
Okay.
Acts on the left ventricular myocardium, and etc.
Yeah.
Arterioles. Actually, no, that's blood pressure, but
Yeah, this is a simple question. What's causing heart rate submax to increase during exercise? We have a whole graph for that. Decrease in parasympathetic nervous system activity and decrease in vagal tone. Increase in sympathetic nervous system activity, specifically sympathetic cardiac nerve and epinephrine acting on the SAE node, increasing heart rate. You guys need to make that connection. This is not new information. We've already talked about increases in heart rate during exercise. Make the connection. Okay? What is happening to stroke volume submax as exercise intensity increases? Increase, decrease, or stay the same?
Increase.
Roxanne, why?
Because it needs to pump more blood throughout the body to bring more oxygen to the exercising muscles.
I want a physiological explanation.
Because the epinephrine is acting on the left ventricular myocardium, causing a greater contraction, which would pump more blood into the aorta.
Okay.
There's another one too, and it's spacing on it right now.
Gwen, can you help with this? What's causing the increases in stroke volume? Oh, sorry, this should say submax.
Increased venous return, increased left ventricular distensibility, increased left ventricular contractility, and decreased resistance.
Yes, sorry, I accidentally erased all of that. Cardiac output equals heart rate, cardiac output, submax equals heart rate submax times stroke volume submax. So as exercise intensity is increasing, heart rate submax is increasing, you should be able to explain to me why. Stroke volume submax is increasing, you should be able to explain to me why. The short version was an increase in end diastolic volume because of an increase in venous return and left ventricular distensibility, and a decrease in end systolic volume due to an increase in left ventricular contractility and a decrease in resistance. That was the short answer to that question. And we have a whole map that goes with that. Okay, so we talked about what's causing the increases in submax heart rate. We talked about what's causing the increases in submax stroke volume. Cardiac output submax is increasing because heart rate submax is increasing and stroke volume submax is increasing. Do you understand how to connect those concepts? So explaining the increases in cardiac output submax involves explaining the increases in heart rate and stroke volume. You've got to make that connection. What time is it? VO2 max. I'm going to stop there. Okay, we finished one side of the table. We'll finish the other side of the table in the next lecture. Okay, so this is where we're starting to talk about what's happening in the body during exercise, which is what we've been leading up to this entire semester. What's happening in the body during exercise. When we get to what happens to the body as a result of training, that's when you're going to be most interested, but we're getting there. I promise. Okay, but you've got to start making connections. All of this information is now going to come together. Okay, so you can't compartmentalize anymore. Memorize this topic, memorize this process, memorize this word. We've got to bring them together and use them now. Okay, you guys have any questions for me?
Oh, I have one question. Is that the main thing that you see people struggling with, is like lacking the connections? Like they'll learn the concepts and then when they get to this part, they're just not able to follow it all the way through?
Absolutely, it's the critical thinking that's lacking, because I know I can give you guys those maps and tell you you need to memorize them, and you can memorize them, no problem. But can you apply them? If I give you an exercise situation, can you apply what's happening to the person's heart rate and why? What's happening to their stroke volume and why? We're going to get to lactate threshold. Start to think about how this is going to affect their lactate threshold, their VO2 max. Look at all the things on the other page and see if you can figure them out before we talk about them. Okay, what if we add fatigue to this? What if we add reflexes to this? Okay, you've got to be able to apply it. That's the whole point. Okay, so we're getting there. We're going to work on the critical thinking. Okay, Tatiana, you have a question?
Yeah, what was the reason vasodilation and vasoconstriction were occurring at the same time again during
So
exercise?
they're both triggered during exercise,
Right.
but at different places in the body. So we're going to have vasodilation at the exercising muscle due to arterial autoregulation and sympatholysis. We're going to have vasodilation of the vessels near the skin for thermoregulation, and have vasoconstriction everywhere else because of epinephrine. So both things are occurring at the same time. They're both contributing to the increases in stroke volume in different ways.
Okay, thank you.
And I really like that as an exam question.
So would a good example for that be the example that you used during the first part of the semester with the marker, where we don't use everything, all our power for that marker where we would for a larger?
I'm not sure how that's related to this.
Okay. I don't know.
Now, you might be thinking of something I'm not thinking of. But that had more to do with the all or none principle and muscle fiber distribution and muscle fiber recruitment patterns, size principle of orderly recruitment. Right now we're talking about responses to acute endurance exercise. Okay, Tatiana, I don't know if this is an old hand up or a new hand up.
Oh, sorry. I'll put it down.
Okay, any other questions for me? I should have your exams graded by Monday. And we can talk about the grades at that point. Okay, so I'll stay on for a couple more minutes if you guys want to ask me questions. I also have office hours at 11, but I know that some of you are going to a workshop. So otherwise, have a good day, have a good weekend. Please study this over the weekend, okay? Especially your terminology if you're uncomfortable with it still. Okay, and I'll see you guys Monday.
Thank you, Professor. I'll talk to you later.
Okay, thank you.
Thank you.